students, and welcome to this 7th lecture of the heat transfer course EEAQ 3235. Today we're going to have a look at heat transfer in extended bodies that are otherwise called fins. Sometimes there occur situations whereby the available surface area or heat transfer area is inadequate to effect the required heat transfer given a certain temperature drop and a heat transfer coefficient. Now, to mitigate or to take care of such a case, extended surfaces are used. Have an example of a case of good application of extended surface, as can be seen there in this picture. Here we have a cylinder of an air-cooled engine. As you can see, here we have our extended surfaces, and also up there we have some more extended surfaces. So this is a good example of good applications of the theory or extended surfaces or bodies. And we have a number of configurations for such extended bodies, and I have four configurations here which are the most common. All right, so we have for A we have a straight uniform cross-section fins. B, we have straight variable fins. Then we have C, what we refer to as annular fins, and D, we call them pin or pin fins. Pin fins. So now we are going to have a look at the theory behind the heat transfer in extended bodies, and we'll be looking at a general case as shown, where the section has a variable cross-sectional area. Now supposing we have this as our main body from which we want to transfer heat through. We have our fin there that has a changing cross-section, and we are taking an infinitely small section of that fin at a distance x, that distance there from the main body, or from the root or the base of the fin, x, such that this small section has a thickness of dx. This is the surface area from which heat will be transferred by convection to the atmosphere or to the surroundings. There will be heat flow by conduction from that body into the control volume, and some heat outflow from the control volume to the rest part, or to the rest part of the fin, and to the atmosphere or to the surroundings. Now, the law of conservation of energy energy for the infinitely small control volume is that Qx, which is an influx, is equals to Qx plus a dx, which is an outflux, plus dq convection. That is for the small area. Now, from the Fourier's law, Qx is equals to minus k, which is the conductivity, area C, that is the area perpendicular to the direction of heat of flow, times dt by dx. And a Qx plus dx is equals to Qx plus the rate of change of Q in the x direction by dx multiplied by dx. So we have Qx plus dx is equals to Qx plus dq x by dx times dx, which is equals to minus ka c dt by dx minus k d dx rub into bracket ac times dt by dx, and we are multiplying that by dx. So now the conservation equation becomes a Qx, which is minus k ac dt by dx is equals to minus ka c dt by dx minus k dx ac dt by dx times dx plus now dq convection. So as you can see, that and that cancels out, and we're left with 0 is equals to minus k dou x of ac dt by dx plus dq small convective heat outflow, which is the same as h times a das times a t minus a ts, where ts is the temperature of the surroundings and t is the temperature of the fin at the small cross section. So we can say minus k dou x of ac dt by dx plus h das t minus ts is equals to 0. Okay, or we can put it this way. K dou x AC dt by dx minus h das t minus ts is equals to 0. And now I can divide through by k, and if I divide through by k, I get dou x of AC dt by dx minus das times h times t minus ts, all of that divided by k, and that is equals to 0. Now I can now carry out this operation here, this one here, using the product rule. So I have dAC by dx times dt by dx plus d squared t by dx times AC, okay, and all of that is multiplied by dx minus h das over k t minus ts, which is equals to 0. Dividing through by dx, I have dAC dx times dt by dx plus d squared t by dx, this is squared, AC minus h das over k dx t minus ts is equals to 0. Now also this gives us the general equation for heat flow through an extended surface, and we can derive from it other equations depending on the configuration of the extended surface that we're looking at. So let us have a look first at extended surfaces that have uniform cross-section. So if our fin has a uniform cross-section, it means that a dAC by dx is equals to 0, right? And we can also say that dAS will then be equal to a constant perimeter times the thickness of our elemental body. So this will give us an area of PDS. So our equation reduces to d squared t dx squared times AC minus h. Instead of dAS, we'll put p dx, and we're dividing by k, and we're dividing again by dx and multiplying by t minus ts, and all of that is equals to 0. dividing through by AC, we have d2t dx squared minus hp divided by k AC is equals to times t times t minus ts is equals to 0. Now let such that if you differentiate with respect to x, you get dt by dx minus dts by dx is equals to 0, is equals to d theta by dx. So this becomes dt by dx. dts by dx is 0 because ts is a constant. So this is equals to d theta by dx. And it also follows that if you differentiate that expression again, you'll get by dx squared is equals to d squared theta by dx squared. So I can substitute in my equation and get d squared dx squared theta minus hp over kac theta is equals to 0. Now for some good reasons that we'll see later, let us put hp over kac to be equal to m squared, such that now our equation comes to d squared theta by dx squared minus m squared theta is equals to 0. Now because of our wise choice of our constant m squared, we've come up with a differential equation whereby it is linear, homogeneous, second order differential equation, which is very solvable. And the solution in general of that differential equation is theta in the direction of x is equals to a raised to the power of mx times a constant c1 plus c2 e raised to the power of minus mx. So to go a step further, we need to evaluate the constants c1 and c2 are given c1 and c2 given some boundary conditions, and we'll come up with these boundary conditions by having a look at 3 cases. Case 1, where the fin is assumed to be infinitely long. Case 2, where we look at a fin that loses no heat energy from its ends, i.e. it is insulated at that end. And case 3, whereby we'll look at a fin with a finite length. And now let us have a look at our first case. That is whereby we consider a fin that has an infinitely, or it is of an infinite length. So that will give us the temperature profile there. And at that position, when x is equals to 0, T is equals to T naught. And at that position, when x is equals to L is equals to infinity, T is equals to Ts. Now, so we have come up with our set of boundary conditions, and this set of boundary conditions are: 1, at x is equals to 0, T is equals to T naught, such that now we have a temperature difference of T naught minus Ts, and we will denote that by theta naught. For the second condition, boundary conditions, we have at x is equals to L is equals to infinity, T is equals to Ts, such that now the temperature difference is Ts minus Ts, which is equals to 0. So applying our boundary conditions, 1, we have theta, the general equation is theta is equals to C1 EMX plus C2 E minus MX. So when x is equals to 0, theta is equals to theta naught, right, which is also equal to T naught minus Ts, which is equals to C1 E raised to the power of 0 plus C2 E raised to the power of 0. So it means that theta naught is equals to C1 plus C2. Now, applying the second boundary conditions, we have x at x is equals to L is equals to infinity. We have theta is equals to 0, which is equals to C1 e raised to the power of m times infinity plus C2 e raised to the power of minus m times infinity. But you know that e raised to the power of minus m times infinity is a 0, so it implies that 0 is equals to C1 e m infinity, which implies further that C1 is equals to 0. And this means that theta naught is equals to C2, since C1 plus C2 is a theta naught. So we can now go back to our equation, our general equation, and say that theta is equals to C1, and we have seen that C1 is equals to 0 times plus theta 2 C2, and we have seen that C2 is theta naught e raised to the power of minus mx. So theta divided by theta naught is equals to e raised to the power of minus mx. And this means that our temperature distribution T minus Ts divided by T naught minus Ts is equals to E minus mx. That is our temperature distribution. Now, T minus Ts is equals to T naught minus Ts E minus mx. Differentiating the expression, we get dt by dx minus dts dx, which is 0, is equals to T naught minus Ts, which is a constant, dx of E minus mx. So this means that dt by dx is equals to T naught minus Ts minus m e raised to the power of minus mx. Now let us evaluate dt dx at x is equals to 0, and this will give us T naught minus Ts times m, because e raised to the power of minus mx will be e raised to the power of 0, which is 1. Now, this implies that the rate equation of heat flow is, from the Fourier's law, Q is equals to minus K area C times now dt by dx evaluated at x is equals to 0. So Q naught minus Ts m times, there is a minus there, times minus K A C. So Q is equals to K A C M T naught minus Ts. Uses our rate equation for heat transfer. Now, Q is equals to K A C, but M is equals to the square root of Kp. This is to the power of Hp, over KAC, now multiplied by T naught minus Ts. and that can simplify further to the square root of KACHP T naught minus TS. So bearing that in mind, we can have a look at an example, and the example reads, example 1, calculate the amount of energy required to weld two naked copper wires together, each of 1.5 millimeters in diameter, and you're told that the solder and the solder melts at 190 degrees C. And then you're told that the wires are vertical and in air, that is at 28 degrees C. And you're told to take H is equals to 20 watt per meter squared Kelvin, and K is equals to 330 watt per meter Kelvin. So let us have a look at the solution. So we'll first start by having a look at the area, and the area is pi by 4 times d squared, which is equals to pi by 4 times 0.0015 squared, which is equals to 1.767 times 10 to the power of negative 6 meters squared. And now we can also calculate the perimeter, which is equals to pi d, which is equals to pi times 0.0015, and that is equals to 4.712 times 10 to the power of negative 3 meters. So now we can go ahead and calculate the rate of heat flow, which is equals to the square root of H rho HP KAC times T naught minus TS, and this is equals to H 20 times 330 times P, and P is 4.7 1.712 times 10 to the power of negative 3 times 1.767 times 10 to the power of negative 6 square root times 190 minus 20. And using your calculator, you can evaluate that, and you see that it is equals to 1.26 watt. That is for each wire, but we have two wires, so for 2 wires it is equals to 1.26 times 2, which is equals to 2.52 watts. Now let's have a look at another example. And it reads, a temperature rise of 60 degrees in a circular shaft is caused by the amount of heat generated due to friction in the bearings, in the bearing. Mounted on the shaft. The thermal conductivity of the shaft material is 50 watt per meter Kelvin, and the heat transfer coefficient is 6.5 watt per meter squared Kelvin. So it is required of us to develop an expression for the temperature distribution, and B, to determine the amount of heat transferred through the shaft. So we have our equation that we've already derived, that is theta r over theta naught is equals to E minus mx. So that equation is what was required in our part A. And part B, we're supposed to calculate the amount of heat transferred, the rate of heat transferred, and that is given by Q minus KAC dt by dx evaluated at x is equals to 0, and we saw that that is equals to the square root of K ACHP times a T naught minus TS. So for this particular case, this is equals to, that is equals to K, which is 50 times area C times H, which is 6.5 times the perimeter P, square root times 60 minus, okay, the temperature rise, T naught minus TS is equals to 60. So times, okay, that is okay. So that is T naught minus that, and this is times 60. Now area C is equals to pi d squared over 4, and the perimeter P is equals to pi d. So this is equals to pi by 4 times the diameter, and the diameter is 0.06 squared, okay, and P is equals to pi times 0.06. So plowing them back into our equation, we have Q is equals to 50 times 6.5 times pi by 4 times 0.06 squared times pi times 0.06 square root times 60, and that gives us a figure of 24.97 watt. Thanks.